Imagine you're about to embark on a journey so vast that if you traveled at the speed of light, 186,282 miles per second, it would take you 93 billion years just to cross the observable universe once. Now imagine actually visiting every single galaxy in that universe. What if I told you that the journey I'm about to take you on will reveal something so fundamentally strange about reality that by the end, you'll question whether distance even means what you think it means? Here's the mind-blowing part that most people don't know. When we look at distant galaxies, we're not just seeing them as they were in the past. We're actually seeing different versions of the same fundamental structures, repeated across cosmic time like echoes. The universe doesn't just contain galaxies scattered through space. It contains the entire history of galaxy formation, frozen in light, all visible at once. You're about to discover that flying through every galaxy in our observable universe isn't just a journey through space. It's a journey through 13.8 billion years of cosmic evolution. And what awaits at the edge will completely reframe everything you thought you knew about existence itself. But before we launch into this cosmic odyssey, I need you to do something for me. Hit that like button right now, because what you're about to learn will change how you see the night sky forever. Subscribe and turn on notifications, because we're diving deep into territories most science channels won't touch. And here's what I'm curious about. Drop a comment telling me which country you're watching from, and what time it is, where you are right now. Why? Because as we're about to discover, the very concept of now becomes meaningless when we're dealing with cosmic distances. Your now and the now of a galaxy 10 billion light years away are completely different moments in the universe's history. Let that sink in. Let's start with the basics, but I promise you, even these foundations will twist your understanding of reality. Our observable universe contains approximately 2 trillion galaxies. That's a 2 followed by 12 zeros. But here's the first twist that most people miss. This number is actually decreasing. Every second that passes, galaxies are disappearing from our observable universe forever, crossing beyond an invisible boundary called the cosmological event horizon. We're living in a shrinking observable universe, and by the time you finish watching this video, several dozen galaxies will have been lost to us forever. To understand our journey, we need to define what we mean by observable universe. It's not just the distance light has traveled since the Big Bang. That would be 13.8 billion light years, right? Wrong. Due to cosmic expansion, the observable universe has a radius of about 46.5 billion light years. This seems impossible. How can we see something 46.5 billion light years away if the universe is only 13.8 billion years old? Think of it like this. Imagine you're on a massive conveyor belt, and you throw a ball forward. While the ball is traveling through the air, the conveyor belt is also moving, carrying both you and the ball. By the time the ball lands, the distance between you and the landing spot is much greater than the ball actually traveled through the air. Space itself has been expanding while light has been traveling toward us, stretching the distance. Now here's where it gets wild. Astronomer Edwin Hubble, yes, the telescope's namesake, discovered in 1929 that galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, called Hubble's law, revealed that the universe itself is expanding. But in 1998, astronomers Saul Perlmutter, Brian Schmidt, and Adam Rees made a discovery that won them the 2011 Nobel Prize in Physics and completely upended our understanding. The universe's expansion is accelerating. There's something out there, something we've labeled dark energy, that comprises about 68% of the universe's total energy and is pushing galaxies apart faster and faster. Here's why this matters for our journey. It means that the galaxies we're going to visit are arranged not just by distance, but by velocity. The farther we travel, the faster those galaxies are receding from us. until we reach a point where they're moving away faster than the speed of light. Yes, you heard that right, faster than light. This doesn't violate Einstein's special relativity, because it's not the galaxies moving through space faster than light, it's space itself expanding. Think of it like dots on a balloon that's being inflated. The dots aren't moving across the rubber, but as the rubber expands, they get farther apart. Let me paint you a picture of the cosmic neighborhood we're about to leave. Earth sits in the Milky Way galaxy, a barred spiral galaxy containing between 100 and 400 billion stars. Our Sun is located about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Arm. The Milky Way is just one galaxy in a collection called the Local Group, which contains about 80 galaxies, including our nearest major neighbor, the Andromeda Galaxy, which is speeding toward us at 68 miles per second. In about 4.5 billion years, Andromeda and the Milky Way will collide and merge, but we won't be here for our journey, because we're going to fly through every galaxy, starting right now. Our journey begins. As we accelerate away from Earth, the first galaxies we encounter are the Milky Way's satellite galaxies. The large and small Magellanic Clouds hang in the southern sky, visible to observers in the southern hemisphere as fuzzy patches of light. These irregular dwarf galaxies orbit our Milky Way like moons around a planet. And here's something incredible. They're being torn apart by our galaxy's gravitational pull. Long streams of gas called the Magellanic Stream trail behind them like cosmic breadcrumbs, stretching across 600,000 light-years of space. We're witnessing galactic cannibalism in real time. Flying through the large Magellanic Cloud at 160,000 light-years from Earth, we pass through regions of active star formation, like the Tarantula Nebula, the most luminous and active star-forming region in our local group of galaxies. If this nebula were as close to Earth as the Orion Nebula 1 of our nearest star-forming regions, it would cast shadows at night. Think about that. A nebula bright enough to make shadows. But here's the revelation that's going to start bending your mind. As we travel farther from Earth, we're not just moving through space, we're moving through time. The light we see from the large Magellanic Cloud left that galaxy 160,000 years ago, when Homo sapiens were just beginning to migrate out of Africa. When we actually arrive at the large Magellanic Cloud on our journey, we're seeing it as it is now, but Earth observers looking at it are seeing it as it was 160,000 years ago. The concept of simultaneity of events happening at the same time begins to break down across cosmic distances. There is no universal now. Your present moment is not the same as the present moment in another galaxy. Time itself fragments across the cosmos. We push onward through the local group, our cosmic backyard containing about 80 galaxies within a region roughly 10 million light-years across. Next up is the Andromeda Galaxy, M31, at 2.5 million light-years away. As we approach, the sheer scale becomes overwhelming. Andromeda contains approximately 1 trillion stars, more than double the Milky Way's stellar population. It's so massive and close that if your eyes were sensitive enough, it would appear 6 times wider than the full moon in Earth's night sky. Flying through Andromeda's spiral arms, we witness something extraordinary. Unlike the Milky Way, Andromeda has a double nucleus at its core, 2 bright points of light where we'd expect one. This isn't 2 supermassive black holes, but rather the remnant of an ancient galactic collision. Andromeda, like the Milky Way, is a cannibal. It's consumed multiple smaller galaxies over billions of years, and the evidence is written in stellar streams and disrupted orbits. We're flying through a crime scene of cosmic proportions. Here's where things get philosophically strange. As we fly through Andromeda at what we'll call now in our journey, observers on Earth are seeing Andromeda as it was 2.5 million years ago, before humans existed. The light reaching Earth left Andromeda when Australopithecines were walking upright in Africa. But in our ship, traveling through Andromeda right now, We could look back at Earth, and if we had a powerful enough telescope, see Earth as it was 2.5 million years ago. We'd see our own planet's past. Time becomes spatial. Distance becomes temporal. The further we travel, the more these concepts interweave until they're inseparable. We continue through the local group, visiting the Triangulum Galaxy, M33, a beautiful spiral located 3 million light-years away. This galaxy has been a gift to astronomers. It's close enough to resolve individual stars and nebulae, making it a cosmic laboratory for studying star formation and galactic structure. But what's fascinating is what we don't see here. There's no evidence of a supermassive black hole at Triangulum's center. This is unusual. Most galaxies harbor supermassive black holes millions to billions of times the sun's mass at their cores. Triangulum might be the exception that proves the rule, or perhaps its central black hole is just quieter, having consumed all the nearby matter already. As we reach the edge of the local group, at about 5 million light-years from Earth, we need to talk about what we're actually going to see on this journey, because here's where reality gets counterintuitive. When we fly through a galaxy, what are we actually experiencing? Galaxies aren't solid objects. They're mostly empty space. The distance between stars in a galaxy is vast. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. If you shrunk the Sun to the size of a basketball, Proxima Centauri would be another basketball located in a different state, thousands of miles away. So flying through a galaxy means passing through a volume of space containing stars, gas, and dust, but mostly just empty space pervaded by gravity and magnetic fields. What we would actually see is a changing sky. Stars would shift position as we move through the galaxy, creating new constellations that no human has ever witnessed. Gas nebulae would appear and disappear as our perspective changes. And if we passed close to any star, we'd see it brighten dramatically as we approached, then dim as we receded, a personal experience of the inverse square law of light. Now we leave the local group and enter the realm of the Virgo supercluster, an enormous structure containing at least 100 galaxy groups and clusters, stretching across 110 million light-years. The local group is just one tiny component of this vast structure, and we're speeding toward its heart, the Virgo cluster, located about 65 million light-years from Earth. But I need to pause here and tell you something that's going to blow your mind. Remember how I said we're going to fly through every galaxy in the observable universe? There are about 2 trillion galaxies. Even if we only spent 1 second in each galaxy, this journey would take 63,000 years. If we traveled at the speed of light, the cosmic speed limit, and could somehow magically teleport instantly from one galaxy to the next with no travel time between them, we'd still be at this for decades. So what we're really discussing here is a thought experiment, a way of organizing our understanding of the universe's structure by imagining what such a journey would reveal. The journey is impossible, but the truths we'll discover are very, very real. Think of this like reading a history book. You can't actually go back in time and visit ancient Rome, but by organizing historical knowledge chronologically, you gain insights into how civilizations evolved. Similarly, by organizing our journey through galaxies from nearest to farthest, we're essentially traveling through cosmic history, from the relatively recent past to the ancient early universe. Each galaxy we visit tells us something about a different epoch in cosmic evolution. As we approach the Virgo cluster, the density of galaxies increases dramatically. This cluster contains between 1,300 and 2,000 galaxies, packed into a region only 15 million light-years across. That might sound spacious, but it's incredibly dense by cosmic standards. Here, galaxy collisions and interactions are common. We're entering a cosmic battleground. At the heart of the Virgo cluster sits M87, a supergiant elliptical galaxy and one of the most massive galaxies in the local universe. M87 is famous for one specific reason. In April 2019, the Event Horizon Telescope collaboration led by astronomers including Katie Bowman and Shepard Dolman, released the first ever direct image of a black hole's event horizon. And it was M87 Central Supermassive Black Hole they captured. This monster contains 6.5 billion times the mass of our Sun and launches a relativistic jet of plasma that extends 5,000 light-years into space. Flying through M87, we'd witness something no human has ever seen up close: the accretion disk around a supermassive black hole. Matter spiraling into the black hole heats up to billions of degrees, glowing brighter than the entire galaxy. The physics here are extreme. Time itself slows down near the event horizon due to gravitational time dilation. If we could somehow hover just outside the event horizon and watch the rest of the universe, we'd see time speed up. Stars would be born, live, and die in fast forward. Galaxies would evolve before our eyes. We'd be watching the universe age. But we can't linger. There are 2 trillion galaxies to visit, and we've barely left our cosmic neighborhood. As we exit the Virgo cluster, something strange begins to happen. The galaxies around us are all moving away, receding into the distance at ever-increasing speeds. We've now traveled 65 million light-years from Earth, and Hubble's law is becoming apparent in our journey. The expansion of space isn't something that happens out there. It's something that's happening everywhere, all the time, even in the space between your atoms. It's just that on small scales, other forces like electromagnetism and gravity are far stronger and hold things together. Here's the equation that governs what we're experiencing. V equals h times d, where v is the recession velocity, d is the distance, and h is the Hubble constant, currently measured at about 70 kilometers per second per megaparsec. What this means is that for every 3.26 million light-years of distance, galaxies are receding about 70 kilometers per second faster. At 65 million light-years from Earth, galaxies are receding at roughly 1,400 kilometers per second. That's over 3 million miles per hour. We press deeper into the cosmos, flying through the massive galaxy clusters that make up the Virgo supercluster. Each cluster contains hundreds to thousands of galaxies, and each galaxy contains billions to trillions of stars. The numbers become meaningless, too large for human comprehension. But here's what you need to understand. We're still in the cosmic shallow end. The Virgo supercluster, vast as it is just one of millions of superclusters in the observable universe. At about 250 million light-years from Earth, we encounter the Coma cluster, one of the richest galaxy clusters known, containing over 1,000 identified galaxies. This cluster is historic. We're now 500 million light-years from Earth, and I want you to pause and really think about what this means. The light we're seeing from galaxies at this distance left them 500 million years ago, during the Cambrian period on Earth, when complex multicellular life was just beginning to explode in diversity in Earth's oceans. No vertebrates had yet ventured onto land. No plants grew on the continents. And yet, photons were leaving these distant galaxies, traveling through the expanding void, waiting for 500 million years to eventually arrive at our eyes. But in our imaginary spacecraft, we're there now. We're seeing these galaxies as they exist now, roughly 13.8 billion years after the Big Bang. And here's the twist. If we looked back at Earth with a sufficiently powerful telescope, we'd see Earth during the Cambrian period. We'd see trilobites crawling along ancient seabeds. We'd see the Sun as it was 500 million years ago, slightly dimmer and younger than it is today. Our location in space determines our view through time. Every place in the universe has a different now, a different temporal perspective on cosmic history. This is why astronomers talk about looking back in time when they observe distant objects. It's not a metaphor, it's literal. The farther out we look, the farther back in time we see. And on our journey, as we travel outward through space, we're effectively traveling forward through cosmic time, visiting galaxies that exist progressively later in the universe's history. But observers on Earth, looking at these distant galaxies, see them as they were in progressively earlier epochs. At 1 billion light-years from Earth, we're leaving behind the familiar structures of the nearby universe. We're no longer in the Virgo supercluster. We're flying through a region of space that contains thousands of superclusters, each containing thousands of clusters, each containing thousands of galaxies. The scale is becoming incomprehensible, but the universe has structure on even larger scales. In the 1980s, astronomers Margaret Geller and John Huckra conducted the first large-scale mapping of galaxy positions and discovered something shocking. Galaxies aren't distributed randomly through space. They're arranged in enormous walls, filaments, and sheets surrounding vast empty regions called voids. The universe has a cosmic web structure, with galaxies strung along filaments of dark matter like lights on a spider's web. As we continue our journey, flying through superclusters, we're essentially traveling along these filaments. The Sloan Great Wall, discovered in 2003, is one of the largest structures in the observable universe, a vast sheet of galaxies stretching 1.37 billion light-years across. Flying through, it would take over 1 billion years at light speed, passing through countless galaxy clusters. Here's the profound implication. Structure in the universe exists on scales approaching the size of the observable universe itself. There are patterns and organizations that span billions of light years. This tells us something fundamental about how the universe formed. These structures grew from tiny quantum fluctuations in the early universe, ripples in the density of matter that were stretched to cosmic scales during a period of rapid inflation in the first fraction of a second after the Big Bang. Think of it like this. Imagine you have a balloon with tiny wrinkles on its surface. Now imagine inflating that balloon to the size of a house, and a city, and a planet. Those tiny wrinkles would become enormous ridges and valleys. That's essentially what happened to quantum fluctuations in the early universe. They were inflated to cosmic scales, creating the seeds of all structure we see today. At 2 billion light-years from Earth, we're seeing galaxies as they were when the first dinosaurs were appearing on Earth during the Triassic period. But there's something else happening at this distance. The galaxies start to look different. We're beginning to see changes in galactic structure and composition that reflect cosmic evolution. You see, galaxies weren't always as they are today. In the early universe, galaxies were smaller, more chaotic, and full of gas that would eventually form stars. The first galaxies were irregular dwarf galaxies that merged over billions of years to form the large spiral and elliptical galaxies we see nearby. As we journey outward and look farther back in time, we're witnessing galactic archaeology, seeing earlier stages of galactic evolution frozen in light. We've now traveled 3 billion light-years from Earth, and we need to talk about something extraordinary. At this distance, we're beginning to encounter quasars quasi-stellar, objects that appear point-like in telescopes, but are actually supermassive black holes at the centers of young galaxies, actively consuming enormous amounts of matter and radiating energy, equivalent to trillions of suns. Quasars were first identified as mysterious radio sources in the 1950s and 60s. In 1963, astronomer Martin Schmidt measured the spectrum of a quasar called 3C273 and made a shocking discovery. Its spectral lines were shifted dramatically toward the red end of the spectrum, indicating it was receding at 16% the speed of light. This meant it was incredibly distant, about 2.5 billion light-years away. But for it to be visible at such a distance, it had to be extraordinarily luminous. It was shining with the light of 4 trillion suns, all from a region smaller than our solar system. Flying through a quasar-host galaxy would be lethal. The radiation environment near an actively feeding supermassive black hole is so intense that it would fry any biological life and probably vaporize any spacecraft. The accretion disk glows with temperatures in the millions of degrees, and relativistic jets shoot matter outward at nearly the speed of light, powered by magnetic fields twisted around the black hole. This is the universe at its most violent and energetic. What's fascinating is that quasars are rare in the nearby universe, but increasingly common as we look farther back in time. Most quasars existed when the universe was between 1 and 3 billion years old. This tells us that supermassive black holes grew rapidly in the early universe, feeding voraciously on available gas. But as galaxies matured and consumed or expelled their gas supplies, the black holes went quiet. The Milky Way's central black hole, Sagittarius A*, is dormant. Now, it's not a quasar because there's not enough nearby matter to feed it. As we cross the 4 billion light-year mark, I need to tell you something that might be uncomfortable. We're now so far from Earth that if we could somehow instantaneously send a signal back home, which we can't, because nothing travels faster than light, Earth wouldn't exist yet. The light reaching us from Earth at this location shows Earth as it was 4 billion years ago, during the Hadean or early Archean eon, when the planet was a hellish ball of volcanic activity and possibly covered by a global ocean. No continents yet, no oxygen in the atmosphere, just single-celled bacteria eking out an existence in hostile conditions. Your home, from this perspective, is unrecognizable. This is the power of cosmic distance. It doesn't just separate places, it separates times. Every location in the universe is living in its own temporal reference frame, its own now that's different from every other location's now. At 5 billion light years, we're approaching a significant milestone in cosmic history. We're nearing the era when dark energy began to dominate the universe's expansion. Remember how I mentioned earlier that the universe's expansion is accelerating? That acceleration started about 5 to 6 billion years ago, when dark energy, whatever it is, overcame the gravitational pull of matter and began pushing space apart faster and faster. Before this transition, the universe's expansion was decelerating. Gravity was winning, slowing down the expansion rate. But dark energy changed everything. Think of it like a ball thrown upward. Initially, gravity slows the ball down. But imagine if at some point, an anti-gravity force took over and started accelerating the ball upward instead. That's essentially what happened to the universe's expansion. This has profound implications for the fate of the universe. If dark energy continues to dominate, and all evidence suggests it will, then the universe will expand forever, accelerating indefinitely. Eventually, billions of years in the future, the expansion will carry distant galaxies beyond our cosmological event horizon. They'll disappear from view forever, their light too stretched and too far away to ever reach us. The universe will become a lonely place, with only our local gravitationally bound structures, perhaps the merged Milky Way Andromeda galaxy, visible in an otherwise dark sky. We're now 6 billion light years from Earth, halfway across the observable universe, and I need to hit you with something that challenges everything. What if I told you that most of the galaxies in the observable universe are forever unreachable? Even if we could travel at the speed of light starting right now, we could never reach them. The expansion of space is carrying them away faster than we could ever travel toward them. There's a sphere around us, called the Hubble sphere, with a radius of about 14.4 billion light years. Inside this sphere, space is expanding slower than the speed of light. So in principle, if we left right now at light speed, we could eventually reach those galaxies. But beyond the Hubble sphere, space is expanding faster than light, and those galaxies are forever beyond our reach. We can see them, their light can still reach us, because it was emitted when they were closer, but we can never touch them. This means the observable universe contains regions that are causally disconnected from us. There are galaxies we can see, but never reach, places where events are happening that can never influence our future, no matter how long we wait. The universe is fundamentally divided into regions that can affect each other, and regions that can't. And as time goes on, and the universe continues to expand, more and more galaxies cross beyond the Hubble sphere, leaving us forever. At 7 billion light-years from Earth, we're seeing galaxies as they were when the universe was only about half its current age. These galaxies look noticeably different from nearby galaxies. They're bluer, indicating more active star formation. They're more irregular in shape, still settling into stable structures. We're witnessing cosmic adolescence galaxies in their formative years. This is where we start encountering massive galaxy collisions and mergers with increasing frequency. In the younger universe, galaxies were closer together and interactions were more common. When galaxies collide, they don't actually crash like cars in an accident. Remember, they're mostly empty space. Instead, they pass through each other, but their mutual gravitational pull distorts their shapes, triggers massive bursts of star formation, and eventually causes them to merge into single, larger galaxies. One of the most famous examples is the antennae galaxies, two spiral galaxies that began colliding a few 100 million years ago. Long tidal tails of stars and gas stream outward from the collision site, resembling insect antennae. Flying through such a collision would be spectacular. The sky would be ablaze with newborn stars and glowing gas clouds. Gravitational forces would be tearing apart star clusters and flinging them into intergalactic space. At 8 billion light-years, we need to address something philosophical. We're now seeing galaxies as they were 8 billion years ago, when the universe was only 5.8 billion years old. Earth didn't exist yet. Our sun didn't exist yet. The solar system wouldn't form for another 3.4 billion years. We're looking at a universe that predates everything familiar. But here's the existential twist. In a sense, this ancient universe is also the real universe. The light from these galaxies is reaching us right now, at this present moment. We're not seeing an illusion or a recording. We're seeing actual photons that have been traveling for 8 billion years. The past is reaching into our present, literally touching our telescopes with light from epochs before our world existed. This raises a profound question. What is reality? Is reality what's happening now, across the universe even though there's no universal now? Or is reality what we can observe and measure, which is always a mixture of different moments from different places? In a universe where simultaneity is relative and observation collapses time and space into a single moment of measurement, reality becomes something far stranger than our intuition suggests. At 9 billion light-years, we're deep into the epoch of peak star formation in the universe's history. Between about 8 and 11 billion years ago, the universe was forming stars at a rate 10 times higher than today. Most of the stars that will ever exist were born during this era. We're flying through a universe in its prime, a cosmic rush hour of stellar birth. The galaxies here are furiously churning out stars, consuming their gas supplies at prodigious rates. The night sky of a planet in one of these galaxies would be dramatically brighter than Earth's, filled with brilliant blue stars and glowing nebulae. But it would also be a more dangerous place. Supernovae would be exploding constantly, bathing nearby systems in high-energy radiation. Here's something that should blow your mind. The atoms in your body, the carbon, oxygen, nitrogen, and iron that make up your cells, were almost certainly forged during this epoch of peak star formation. Those atoms were created inside massive stars that lived and died billions of years ago, scattered into space by supernova, eventually incorporated into the molecular cloud that collapsed to form our solar system. You are made of stardust, and most of that stardust was manufactured during the cosmic era we're now flying through. At 10 billion light-years, we're 3/4 of the way to the edge of the observable universe. The galaxies here are smaller, less organized, more chaotic. We're seeing galaxy formation in progress, witnessing the assembly of cosmic structure in real time, or rather, in ancient time, since what we're seeing happened 10 billion years ago. But there's something else happening here that's crucial to understand. At these distances, space itself has expanded so much since the light left these galaxies that their wavelengths have been stretched dramatically. Light that was emitted as ultraviolet or visible light has been stretched into infrared wavelengths. This redshift effect becomes more and more extreme as we journey farther. This is why the James Webb Space Telescope, launched in 2021, was designed to observe primarily in infrared wavelengths. It's specifically built to see these extremely redshifted galaxies from the early universe. The light from these galaxies has been traveling so long that by the time it reaches us, it's been stretched to wavelengths invisible to human eyes. At 11 billion light-years from Earth, we're entering a realm that represents about 80% of cosmic history. We're seeing galaxies as they were when the universe was less than 3 billion years old. The changes become more dramatic with each passing billion light-years. Galaxies are smaller, more irregular. Dark matter halos are still assembling. The cosmic web is less defined. But we're also approaching a boundary of a different sort. At these distances, we're nearing the limits of what current technology can observe in detail. The galaxies become fainter, more difficult to study. We're pushing against the observational horizon of human knowledge. Beyond this point, we're entering territories that have only been explored in the last few decades, and there are still many mysteries. At about 11.5 billion light-years, we encounter something remarkable: the first galaxies that look completely alien to our local experience. These are the earliest elliptical galaxies, massive collections of stars that formed incredibly quickly in the early universe. The puzzle here is timing these galaxies assembled faster than our models predicted. How did enough stars form quickly enough to build these massive galaxies so early in cosmic history? It's a question that's still being actively researched. Here's why this matters. It challenges our understanding of galaxy formation. According to the Standard Model, galaxies should build up gradually through the merger of smaller systems. But some of these early massive galaxies seem to have formed in a single rapid burst of star formation. It's like finding a full-grown oak tree in a forest where you expected only saplings. Something about the early universe allowed galaxy formation to proceed faster than we thought possible. At 12 billion light-years, we're now seeing galaxies as they were just 1.8 billion years after the Big Bang. The universe is young here, still working out its structure, and we're about to cross into a region that was completely unknown to humanity until very recently. Before we continue, I want you to pause and think about your own significance in this cosmic context. You're sitting wherever you are right now, maybe in your room, on a bus, at work watching, or listening to a description of a journey across 12 billion light-years of space. The light from the galaxies we're now discussing left them before Earth existed, traveled for 12 billion years through expanding space, and is only now arriving at human telescopes. And yet, you exist. You, a collection of atoms forged in ancient stars, temporarily arranged into a conscious pattern capable of contemplating the universe's vastness. You're made of material that's 13.8 billion years old, organized into a structure that's perhaps a few decades old, thinking thoughts that are milliseconds old, about photons that are billions of years old. Every layer of time, from the age of the universe down to the firing of neurons in your brain, is represented in the single moment of comprehension. This is why you matter. Not because you're cosmically significant in size. You're not. Not because you'll leave a mark on the universe that lasts forever. You won't. You matter because you're a point of self-awareness in the cosmos. You're the universe reflecting on itself, a temporary vortex of complexity where matter and energy organize into something capable of understanding. That's not nothing. That's extraordinary. We're now pushing beyond 12 billion light years, entering what astronomers call the epoch of reionization. This is a crucial transition in cosmic history. In the early universe, about 380,000 years after the Big Bang, the cosmos cooled enough for neutral atoms to form mostly hydrogen and helium. The universe became transparent for the first time, and this is when the cosmic microwave background radiation that we observe today was released. But then came the cosmic dark ages, a period lasting hundreds of millions of years, when the universe was filled with neutral hydrogen gas that absorbed most light. No stars existed yet, no galaxies, just expanding, cooling, neutral gas pervading all of space. Then, somewhere between 150 million and 1 billion years after the Big Bang, the first stars ignited. These weren't like stars today. They were massive, perhaps 100 to 1,000 times the mass of the Sun, composed only of hydrogen and helium, because no heavier elements existed yet. They burned furiously hot and bright, living only a few million years before exploding as supernova. These explosions created the first heavy elements, carbon, oxygen, iron, and scattered them into space, enriching the gas that would form the next generation of stars. More importantly, these first stars emitted intense ultraviolet radiation that began to reionize the hydrogen gas in the universe, stripping electrons from atoms and making the universe transparent again. This process gradually spread outward from each star, creating expanding bubbles of ionized gas that eventually overlapped and merged. By about 1 billion years after the Big Bang, the entire universe was reionized. We're flying through galaxies that existed during this transition period. At 12.5 billion light-years from Earth, we're seeing some of the galaxies responsible for reionization. They're small, irregular, blazing with the light of massive young stars. These galaxies are the pioneers of cosmic structure, the first significant concentrations of matter to collapse under their own gravity and ignite stellar fusion. Here's something that will challenge your assumptions. These earliest galaxies were much smaller and fainter than expected. For years, astronomers searched for the first galaxies and found them surprisingly difficult to detect. When the James Webb Space Telescope began operations in 2022, it discovered numerous very early galaxies, some existing just 300 to 400 million years after the Big Bang. But many of these galaxies are more massive and mature than theoretical models predicted. This created what some astronomers call a crisis in cosmology, not because the Big Bang theory is wrong, but because our models of how quickly galaxies could form and grow may need refinement. The universe seems capable of organizing structure faster than we thought. It's like evolution producing complex organisms much more rapidly than expected. The mechanisms must be more efficient than our calculations suggested. At 13 billion light-years from Earth, we're seeing the universe as it was less than 1 billion years after the Big Bang. Galaxies here are fundamentally different from anything in the local universe. They're forming stars at extreme rates, sometimes hundreds to thousands of solar masses per year, compared to the Milky Way's modest rate of about 1 to 3 solar masses per year. Flying through one of these primordial starburst galaxies would be overwhelming. The density of stars is much higher than in modern galaxies. The sky would be brilliant with young, hot stars. Supernova would explode regularly, perhaps one every century in a single galaxy. The environment would be hostile to life as we know it, bathed in intense radiation and buffeted by supernova shockwaves. But here's the profound realization. This hostile, violent epoch was necessary for life to eventually exist. The heavy elements being forged in these early stars, carbon, nitrogen, oxygen, iron, and all the others, are the raw materials for planets and biology. Without this early era of intense star formation and stellar death, the universe would remain forever composed only of hydrogen and helium. No rocky planets could form. No chemistry complex enough for life could develop. You exist because the early universe was violent. Your atoms were created in cosmic crucibles billions of years before your birth. Every breath you take contains oxygen atoms forged in dying stars during this ancient epoch. Every thought you think runs on electrochemical signals using sodium, potassium, and calcium ions that were manufactured in supernova before the solar system existed. Your existence depends on stellar death. At 13.2 billion light-years, we're approaching the observational frontier. We're seeing galaxies that existed only 600 million years after the Big Bang. This is near the beginning of the epoch of reionization, when the first substantial population of galaxies was just emerging. The cosmic dark ages are ending, and light is conquering the universe. The galaxies here challenge our ability to observe and understand. They're so distant that even their brightest light is stretched in fried wavelengths. Their light has been traveling for so long that the universe has expanded substantially during the journey, making them appear farther away than they were when they emitted the light. And due to the expansion, these galaxies are now actually about 30 billion light years from our current position. We're seeing them where they were 13.2 billion years ago, but they've been carried away by cosmic expansion in the intervening time. This is where the concepts of distance become truly strange. How far away is a galaxy we see at 13.2 billion light years? Is it 13.2 billion light years away, the light travel distance? Or is it 30 billion light years away, its current position? The answer depends on what you mean by distance. Both numbers are correct in different frameworks. There's the comoving distance, the proper distance, the light travel distance, each measuring something different about the vast gulf between here and there. At 13.4 billion light years from Earth, we're seeing galaxies that existed just 400 million years after the Big Bang. We're entering the realm of the earliest galaxies ever observed. These are some of the most distant objects the James Webb Space Telescope has detected faint, reddish smudges and deep images that represent baby galaxies in the cosmic dawn. What's remarkable is that we can see them at all. The light from these galaxies has traveled for over 13 billion years, traversing an expanding universe to reach our telescopes. And that light left these galaxies when they were tiny, perhaps just a few thousand light years across, containing only millions to billions of stars, compared to the hundreds of billions in the Milky Way today. But here's something that should absolutely blow your mind. In the time since this light left these galaxies, they've evolved dramatically. The galaxies we're seeing as small, irregular collections of young stars have, in their own reference frame, aged 13.4 billion years. If we could somehow see them as they exist now in the universe's timeline, they might be massive elliptical galaxies, or they might have merged with other galaxies to form something even larger. Or they might have been torn apart by tidal forces and no longer exist as discrete entities. We're seeing their youth, but they're experiencing their old age. Time is not synchronized across the cosmos. As we push beyond 13.5 billion light years, we need to talk about what happens at the very edge of the observable universe. We're approaching a boundary beyond which we cannot see with conventional telescopes. Not because there's nothing there, but because light from those regions hasn't had time to reach us yet. But wait, there's actually one more thing we can see, and it's the most important observation in all of cosmology. Beyond the most distant galaxies, there's a faint glow of radiation coming from all directions. This is the cosmic microwave background, CMB, the leftover heat from the Big Bang itself, emitted when the universe was only 380,000 years old. At about 13.8 billion light years light travel distance, or 46 billion light years comoving distance, we encounter this wall of light. The CMB represents the surface of last scattering, the moment when the universe became transparent and photons could travel freely through space for the first time. Before this moment, the universe was opaque, a hot plasma where light couldn't travel more than a short distance before being absorbed and re-emitted. The CMB was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate noise from a radio antenna and kept detecting a persistent background signal from all directions. They'd stumbled upon the afterglow of creation itself, earning them the 1978 Nobel Prize in Physics. The CMB appears to us now as microwave radiation with a temperature of 2.725 Kelvin, just a few degrees above absolute zero. But when it was emitted, the universe was about 3,000 Kelvin, hot enough to glow visibly. The expansion of space has cooled and redshifted this radiation over billions of years, stretching its wavelengths from visible light to microwaves. Here's what's profound about the CMB. It's extraordinarily uniform. In every direction we look, it has almost exactly the same temperature. This tells us that the early universe was incredibly smooth and homogeneous. But almost is the key word. The CMB has tiny temperature fluctuations, variations of only about 1 part in 100,000. These tiny ripples represent quantum fluctuations from the earliest moments of the universe that were inflated to cosmic scales. And here's the connection that should make you shiver. Those tiny ripples in the CMB are the seeds of everything. Every galaxy, every star, every planet, every personal of cosmic structure grew from those minute quantum fluctuations 13.8 billion years ago. The pattern of temperature variations in the CMB is like a cosmic blueprint, encoding the future locations of all galaxies and galaxy clusters. You exist because of quantum randomness in the first fraction of a second after the Big Bang. If those quantum fluctuations had been even slightly different, we've now flown through essentially every galaxy in the observable universe, from our nearest neighbors just thousands of light years away to the most distant galaxies at the edge of cosmic visibility. We've traversed 13.8 billion years of cosmic history, from the present day back to the cosmic dawn. But we've hit a wall, the CMB, the edge of the observable universe. What if I told you that this isn't really the edge? The observable universe is just the portion of the universe we can see from Earth. But the universe almost certainly extends far beyond this horizon. In fact, if current inflationary theories are correct, the total universe might be vastly larger than the observable portion, perhaps infinite. Think about what this means. There are regions of space so far away that light from them hasn't reached us yet and never will, due to the accelerating expansion. There might be galaxies beyond our horizon that we'll never know exist. And if the universe is infinite, then somewhere out there, beyond countless horizons, there might be exact copies of you, living identical lives, making identical decisions. This isn't science fiction. It's a serious prediction of cosmological models. The inflationary theory, proposed by Alan Guth in 1980 and refined by Andre Linde, Paul Steinhardt, and others, suggests that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. During this inflation, the universe expanded by at least a factor of 1026 and possibly much more. This expansion was so rapid that regions that were once close enough to be in thermal equilibrium were suddenly separated by vast distances. This explains why the CMB is so uniform. The observable universe all came from a tiny region that was in thermal equilibrium before inflation. But it also means that what we call the universe might just be one small bubble in a vastly larger space. There could be other bubbles, other regions that inflated from different quantum fluctuations, with different physical properties, different constants of nature. This is the controversial idea of the multiverse. I want to pause here and acknowledge that we're entering speculative territory. The multiverse is not an established fact. It's a theoretical prediction of certain models that may or may not be correct. We can't observe other universe bubbles, and it's not clear we ever will. Some physicists embrace the multiverse as a natural consequence of inflation. Others reject it as unfalsifiable speculation that's not really science. But here's why it matters for our journey. It reframes what we've accomplished. We've flown through every galaxy in our observable universe. But if the multiverse is real, we've only explored an infinitesimal fraction of all that exists. Our observable universe, vast as it is, might be just one small patch in an infinite cosmic sea. And yet, even if that's true, our journey has meaning, because the observable universe is all that can ever affect us. Those other universe bubbles, if they exist, are causally disconnected from us. They're not part of our reality in any practical sense. The galaxies we visited on our journey, those are the real universe from our perspective. That's all we have, and it's enough. It's more than enough. It's magnificent. Let me bring this back to something concrete. We started this journey near the Milky Way, our home galaxy, and we've traveled across 13.8 billion years of cosmic history. Along the way, we've seen the local group, our cosmic neighborhood, where galaxies interact gravitationally and sometimes collide, the Virgo supercluster, a vast assembly of galaxy clusters, including our own, the cosmic web, the large-scale structure of the universe with filaments and voids, quasars, the brilliant beacons powered by supermassive black holes in the early universe, the epoch of peak star formation, when the universe was churning out stars at prodigious rates, the earliest galaxies, forming in the cosmic dawn just hundreds of millions of years after the Big Bang, the cosmic microwave background, the afterglow of creation itself. We've witnessed the evolution of cosmic structure from the smooth, nearly uniform early universe to the complex, hierarchical structure we see today. We've seen how tiny quantum fluctuations grew into galaxies and galaxy clusters. We've traced the history of star formation, the creation of heavy elements, and the assembly of the cosmic web. But most importantly, we've seen our place in all of this. Earth is a tiny speck in a galaxy that's one of trillions. Humanity has existed for a cosmic eye blink. Our entire recorded history spans less than 1/1,000,000th of the universe's age. We're insignificant on cosmic scales. And yet, here's the twist that reframes everything. We're also extraordinary. The universe, for most of its existence, was simple. Hydrogen and helium gas, gradually clumping under gravity. Then stars, still relatively simple, just fusion reactions. Then planets more complex, but still just geology and chemistry. But then, on at least one planet, something remarkable happened. The chemistry became so complex that it became self-replicating. Life emerged. Simple at first, just molecules making copies of themselves. But over billions of years, evolution crafted increasingly complex organisms. Eventually, those organisms developed nervous systems, then brains, then consciousness. And finally, after 13.8 billion years of cosmic evolution, the universe produced creatures capable of understanding the universe itself. That's us. We're the universe becoming self-aware. We're matter and energy organized in a way that can contemplate matter and energy. We're the cosmos understanding itself. This is not mysticism. This is simply what happened. The atoms in your brain, forged in ancient stars, arranged in a pattern that can think about ancient stars. The universe has folded back on itself in a strange loop where the observer and the observed are made of the same stuff, governed by the same laws, part of the same system. You might feel insignificant after contemplating the scale of the universe's 2 trillion galaxies, each containing hundreds of billions of stars, scattered across billions of light years. But you shouldn't. You're part of the most complex structures in the known universe. Your brain contains about 86 billion neurons, each connected to thousands of others, forming a network of incomprehensible complexity. The number of possible neural configurations in your brain vastly exceeds the number of atoms in the observable universe. In terms of sheer complexity, you are more sophisticated than a galaxy. A galaxy is mostly empty space with simple objects, stars following predictable orbits under gravity. Your brain is a densely packed information processing system capable of language, mathematics, art, empathy, and self-reflection. From the universe's perspective, you're the more interesting phenomenon. Here's something else to consider. Consciousness might be rare in the universe. We don't know yet. The search for extraterrestrial life continues, but it's possible that intelligent, self-aware life is extraordinarily uncommon. If so, then you're not just a random part of the universe. You're one of the universe's rarest and most precious phenomena. You're one of the few places in the cosmos where the universe can look back at itself and wonder. And even if life is common, even if every other star has a planet with intelligent beings, you're still unique. There will never be another you. Your specific configuration of atoms, your particular pattern of thoughts and memories and personality that exists only once in the history of the universe. When you die, that pattern disappears forever. You're a transient eddy in the cosmic flow, but while you exist, you're unrepeatable and irreplaceable. So what do you do with this knowledge? How does understanding the scale of the universe, the billions of galaxies, and the vast gulfs of space and time change how you live? First, it should give you perspective. Your problems, whatever they are temporary. The universe is 13.8 billion years old and will continue for trillions of years more. Your troubles exist in a tiny sliver of space and time. This doesn't make them unreal or unimportant to you, but it does mean you can hold them a bit more lightly. Nothing human is permanent. All suffering is temporary. All glory is fleeting. Second, it should give you wonder. You live in an age when humans have mapped the observable universe, traced cosmic history back to the first fraction of a second after the Big Bang, and discovered that we're made of recycled stardust. This is astonishing. The night sky isn't just a pretty pattern, it's a deep time archive of cosmic evolution. Every photon hitting your retina has a story spanning billions of years. Third, it should give you responsibility. If consciousness is rare, if self-aware beings are among the universe's most complex and precious phenomena, then we have a duty to preserve and extend consciousness. This means taking care of each other, protecting our planet, and eventually spreading to other worlds. We might be the only beings in our cosmic neighborhood capable of understanding the universe. That makes us valuable beyond measure. And fourth, it should give you connection. The iron in your blood was forged in a massive star that exploded billions of years ago. The calcium in your bones came from a different star. The carbon in your DNA came from yet another. You're not just in the universe, you're the universe. You're not a separate observer looking at the cosmos from outside. You're a part of the cosmos that has temporarily organized itself into a pattern capable of observation. This means you're connected to everything. The atoms in your body have been recycled through countless previous forms: bacterial cells, plants, animals, other human beings. You're made of matter that's 13.8 billion years old, briefly arranged into you, soon to be dispersed and rearranged into something else. You're a temporary pattern in an eternal flow. Let's return to the beginning of our journey and see it with new eyes. We started at Earth, a planet in the Milky Way galaxy, and we've traveled across the observable universe. But now I want you to understand what we've really done. We haven't just traveled through space. We've traveled through time, seeing the universe at different epochs of its evolution. We've seen how structure emerges from simplicity, how complexity grows from quantum fluctuations, how the universe has evolved from a smooth, hot plasma to a rich cosmos full of stars, galaxies, planets, and life. We've also traveled through scales of perspective. We started with the familiar Earth, the Sun, nearby stars, and expanded outward to the incomprehensible superclusters, the cosmic web, the edge of the observable universe. We've seen how our intuitions about space and time break down at cosmic scales, how the universe is stranger than we imagined. And we've traveled through understanding. We started with basic concepts: galaxies, light years, cosmic expansion, and built up to profound insights about dark matter, dark energy, the cosmic microwave background, and the nature of reality itself. We've seen how science has revealed truths about the universe that are more amazing than any mythology. This journey through every galaxy in the observable universe is, in a sense, a journey through human knowledge. Each galaxy we've visited represents discoveries made by astronomers, physicists, and mathematicians over centuries of effort. The universe we've explored is not just the physical cosmos, it's also the universe as understood by human minds. The cosmos is filtered through telescopes and equations and human curiosity. And that brings us to a final, crucial point. This journey isn't over. We've flown through every known galaxy, but there are still mysteries. We don't know what dark matter is. We don't know what dark energy is. We don't know if the universe is finite or infinite. We don't know if there are other universes. We don't know how common life is. We don't know if consciousness exists elsewhere. These are open questions, puzzles waiting to be solved by future generations of scientists. And that's exciting. We're not at the end of discovery. We're barely at the beginning. The next century will likely bring revelations about the universe that we can't even imagine today, just as scientists in 1925 couldn't have imagined dark energy, cosmic inflation, or the discovery of thousands of exoplanets. You're living in an age of cosmic exploration. The James Webb Space Telescope is right now observing the earliest galaxies, studying exoplanet atmospheres, and probing the nature of dark matter. Future telescopes, even larger and more sensitive, are being planned. Missions to explore our solar system are discovering that ocean worlds like Europa and Enceladus might harbor life. The search for extraterrestrial intelligence continues. In your lifetime, we might discover life on another world. We might detect signals from an alien civilization. We might finally understand what dark matter and dark energy are. We might find evidence of extra dimensions or parallel universes. We might solve the mystery of how life began. Any of these discoveries would fundamentally change our understanding of our place in the cosmos. So what I want you to take away from this journey through every galaxy in the observable universe is not just facts about galaxies and cosmic distances. I want you to take away a sense of wonder, a feeling of connection to the cosmos, and an appreciation for how extraordinary it is that you exist and can understand any of this. You're made of atoms that are older than the Earth, temporarily arranged into a conscious being on a planet orbiting an ordinary star in an unremarkable part of an average galaxy in a universe of 2 trillion galaxies. And yet, you're reading this, thinking about this, contemplating the vastness of space and time and your place within it. That's the miracle. Not that the universe is vast. We knew it was vast. The miracle is that something in the universe can comprehend that vastness. The miracle is you. Before we end, I want to address one more thing, the sheer impossibility of what we've just done. We've flown through 2 trillion galaxies. Let me give you a sense of what that actually means. If we had spent just 1 second passing through each galaxy, barely enough time to register its existence, the journey would have taken 63,419 years. Modern humans, Homo sapiens, have only existed for about 300,000 years. Civilization has existed for about 10,000 years. Our hypothetical journey would span recorded human history 6 times over. But 1 second per galaxy is absurdly fast. To actually see anything in a galaxy, to observe stars and nebulae and black holes, we'd need much more time. If we spent just 1 minute per galaxy, the journey would take 3.8 million years. That's longer than humans have existed as a species. If we spent 1 hour per galaxy, examining it in detail, the journey would take 228 million years longer than dinosaurs walked the Earth. And remember, we're not even accounting for travel time between galaxies. Even at the speed of light, crossing from one galaxy to another takes thousands to millions of years, depending on the distance. A realistic journey to every galaxy in the observable universe, traveling at light speed and spending meaningful time at each one, would take trillions of years, far longer than the current age of the universe itself. So what we've done is clearly impossible. This journey is a thought experiment, a way of organizing cosmic knowledge, a mental framework for understanding the structure and scale of the universe. We can't actually make this journey. No one can. The universe is too vast, Time is too short, and the laws of physics won't permit it. But here's the thing. In another sense, we have made this journey. Through telescopes and mathematics, through observation and theory, humanity has explored the entire observable universe. We've seen galaxies at every distance and every epoch. We've mapped the cosmic web. We've traced the history of the universe from the Big Bang to the present day. We've done all of this without leaving Earth. This is the power of science and human curiosity. We might be confined to a tiny planet, but our minds can reach across the universe. We might live for only decades, but we can understand billions of years of cosmic history. We might be made of ordinary matter, but we can theorize about dark matter and dark energy. We transcend our physical limitations through imagination and reason. And that brings us full circle to where we started. At the beginning of this journey, I told you that flying through every galaxy in the observable universe would reveal something fundamentally strange about reality. I promised you that by the end, you'd question whether distance even means what you think it means. So here it is. Distance in the universe isn't just about space. It's about time. It's about causality. It's about which events can influence which other events. Two galaxies separated by billions of light years aren't just far apart in space. They're separated by billions of years of cosmic history. They exist in different temporal reference frames. The distance between them is as much a temporal separation as a spatial one. And here's the deepest insight. The universe doesn't exist as a single, unified now. There's no cosmic present moment that's the same everywhere. Every location has its own now, its own present moment, which is different from every other location's present moment. The universe is not a three-dimensional space, evolving through time. It's a four-dimensional space-time, where past, present, and future all exist in some sense, and where the distinctions between them depend on your reference frame. This is what Einstein's relativity teaches us, and it's confirmed by every observation we make of the cosmos. Time and space are not separate, absolute things. They're woven together into space-time, and they're relative to the observer. Your now is not the same as the now of someone moving at a different velocity, or someone located at a different gravitational potential, or someone billions of light years away. So when we ask, what's happening right now in a galaxy 10 billion light years away, the question doesn't have a single answer. It depends on your reference frame. In one frame, the galaxy might be experiencing one moment. In another frame, it might be experiencing a completely different moment. There's no objective fact about what's happening now across vast cosmic distances. This means that in a very real sense, the past and future are as real as the present. They're just located in different parts of space-time, inaccessible to us due to the structure of causality in the speed of light, but existing nonetheless. The galaxies we've seen on our journey, as they were billions of years ago, those are real, existing moments in space-time, just as real as the now you're experiencing as you engage with these words. The universe is vastly stranger than our everyday experience suggests. And our journey through every galaxy in the observable universe has revealed that strangeness in all its glory. We're at the end now. We've flown through 2 trillion galaxies, crossed 46.5 billion light years of space, traversed 13.8 billion years of cosmic history, and reached the edge of the observable universe at the cosmic microwave background. We've seen the universe evolve from a smooth, hot plasma to a rich cosmos full of structure and complexity. We've witnessed galaxy formation, stellar birth and death, and the creation of the elements that make up planets and life. We've also seen the limits of human knowledge and the frontiers of ongoing research. We've encountered mysteries like dark matter and dark energy that make up 95% of the universe, but remain poorly understood. We've grappled with profound questions about the nature of time, space, causality, and reality itself. And through it all, we've kept returning to one central theme. You, the observer, the conscious being engaging with this information. because that's what makes this journey meaningful. The universe can exist without observers, but it cannot be understood without them. And understanding, consciousness, self-awareness, these are among the most complex and remarkable phenomena in the cosmos. You've now completed a journey through every galaxy in the observable universe. You've seen cosmic history unfold from the Big Bang to the present day. You've grasped concepts that would have been incomprehensible to humans just centuries ago. You've expanded your mind to encompass scales of space and time that dwarf ordinary human experience. And here's my challenge to you. Don't just let this be information. Let it change how you see the world. Tonight, when you look up at the night sky, remember that every point of light has a story spanning billions of years. Remember that you're made of atoms forged in stellar furnaces. Remember that you're part of the universe's ongoing project of becoming self-aware. Let this knowledge give you perspective on your daily concerns, wonder at the cosmos you inhabit, and a sense of responsibility to preserve and extend consciousness into the future. Let it connect you to the deep history of the universe and the potential future that stretches ahead for trillions of years. The universe is vast, ancient, and strange, but it's also beautiful, comprehensible, and in some sense, yours. You're not separate from it, you're an integral part of it. You're what happens when the universe evolves for 13.8 billion years. Matter organizing itself into patterns capable of understanding matter. That's extraordinary. You're extraordinary. Don't forget it. Thank you for joining me on this impossible journey through every galaxy in the observable universe. If this changed your perspective or blew your mind, make sure you're subscribed to this channel for more deep dives into the cosmos. Like this video if you made it to the end seriously. You just spent over 4 hours exploring the universe, and that deserves recognition. And finally, I want to hear from you. Drop a comment right now. What was the most mind-blowing moment in this journey for you? Was it learning that the universe has no universal now? That dark energy makes up 68% of the cosmos? That you're made of stardust forged in the cosmic dawn? Tell me what hit you hardest, and let's keep this conversation going. Remember, you're not just in the universe. You're of the universe. You're the universe experiencing itself. And that makes you cosmically significant, no matter how small you feel. Until next time, keep looking up, keep wondering, and keep exploring. The universe is waiting.